It's nice to be back here. The view is great this morning. So I want to talk about that, geometric enumeration from a quasisymmetric point of view. So what this amounts to is trying to set up an algebraic framework in which certain questions in geometric enumeration have particularly nice descriptions and answers. So I know the phrase set up an algebraic framework is the kind of thing that strikes fear in most audiences of geometers. And for that I apologize. I think if it gets too much, you just sort of go grab a cup of coffee and come back at the end when the geometric consequences will come out and be explicit. Okay, so the basic setup is sort of described in this picture. You know, if you were walking the Berkeley Hills in this direction from left to right, you would know when you're going down and when you're going up. And as a consequence, you know when you've reached the peaks. So a peak is when you've start going down just after you went up. So there's no peak on the far left because you don't really know what happened before, or you just started by going down. But otherwise, every descent preceded by an ascent is a peak. And so this is the theme of this whole talk, is that if you go from descents to peaks, you can get a lot of geometric information, which is not that geometry. But that's the point I'm going to try to make, is this notion of turning descents into peaks enables you to do things like enumerate faces and arrangements starting from the matroid, for example. So this is something we all know about. So in order to talk about this, I need to set it up. And the framework, we're going to live in the land of graded partially ordered sets. You should think your favorite poset perhaps is the face lattice of a polytope, you know, where a poset with a 0 and a 1. The 1 is the entire polytope, the 0 is the empty face, and every other face lies in between these two. And what I want to be doing is counting faces and counting more to the point, counting flags in this poset. So we define this thing called the flag F vector, which is a function on subsets of the so-called active rank. So if this poset has rank n plus 1, then the 1 has rank n plus 1, the 0 has rank 0, and the ranks that count are between 1 and n. And every subset of 1 and n tells me, it indicates a number of flags. Namely, I'm going to count chains in the poset which stop at exactly the ranks that are in the set S. So, for example, if S is a singleton, I'm counting the number of faces of a given dimension. And if we're talking about a face poset of a polytope, say. If S, things like F1, 2, we're shifting by rank. The rank is one more than a dimension. So F1, 2 counts the incidences of vertices on edges. You know, and F1, 3 will count the incidences of vertices on two faces, for example. We collect all that information together, and we want to study this, the behavior of this as a function. The special class of posets we're going to be interested in is so-called Eulerian posets. So they're defined by this relation on the Möbius function, but more to the point, they're defined by this. Namely, these are posets such that for every interval, there's the same number of elements of even rank as odd rank. So that's easy enough to sort of imagine. And basically, these are posets whose order complex has the order characteristic of a sphere. Okay, but this is the going definition. So you take any interval and you count from 0 up to the top, the ranks in even ranks, they're exactly the same number of elements on even and odd rank. So face posets of polytopes and spheres are Eulerian, so that's why we're interested in those. And there is a fact which will sort of be in the background throughout, is that for Eulerian posets, only Fibonacci number of these FSs are linearly independent. Now, there's these numbers. Most of these numbers are dependent on others of these numbers, and then there's a basis consisting of Fibonacci many, which actually give you all the information. And part of the game is how do you express this little information in terms of that many numbers, right? There's 2 to the n numbers, Fs, but only an, Fibonacci number n, which actually count. Okay. So this brings us to something called a CD index, which you may or may not have heard about. It's just a funny way of describing this information, this Fibonacci amount of information. This was a notion that was sort of conceived by Jonathan Fine and developed by Marge Bayer and Andrew Clapper, where they showed that the existence of a CD index is equivalent to exactly what was alluded to on the previous slide, that there are Fibonacci many bits of data in this flag number, in this flag F vector. So in order to say what this thing is, one has to sort of change variables. So we'll define what's called a flag H vector, which is basically a Möbius inversion on the flag F vector. So you just sum over all subsets. To compute HS, you sum over all of its subsets. You add f of t with the appropriate sign. And you get another number. And this is just a different way of expressing the same data. But now you cook it in the following way. You cook it into a generating function on two non-commuting variables, a and b, where you encode the set with an AB word, where in the ith place you put a b if I is in the set, and an A if I is not in the set. I think Richard Ehrenborg told me A stands for absent. So it's a good way to remember it, actually. So if you're not in the set, you get an A, and if you are, you get a B. I'll illustrate this with an example. And then you just write this generating function. You indicate the set with US, and you weight it by that number HS. You add it up. It's a polynomial in two variables, A and B. And the theorem is that this is always a polynomial in C and D, where C is A plus B and D is AB plus BA. And that resulting polynomial is the CD index. So here it is in the simplest case, the face post set of a triangle. Right? Let's try to envision this. You have a triangle. It has one empty set, 3 vertices, 3 edges, and 6 vertex edge incidences. Right? It's just the K33 is the Hasse.
You're putting a lot of weight on it. Maybe it is 7. Look at the, so look at that. Okay? Now, so I maintain that we say we can prove 5 maximum acceleration, but our data indicates that it may be as high as 7. So somewhere in that range is what basically we're pulling out. But we have a data point that's 60 feet away. We could do better if we had more data, but we don't have more data because that's the way the experiment has already been designed. So let's ask this other thing. Now remember I said that the acceleration on a car is monotone decreasing. It starts out real high and then it goes down. So let's try to look at that. So let's fit a smooth curve to the 8 pieces of data and then study the second derivative. Now we're not supposed to do that. You're not supposed to take and fit data and then look at derivatives. That's unbounded. You can look at integrals. That's bounded, right? But we have no choice. That's all we can do. So we fit data and then look at derivatives. Oh, we had to pay an awful price. Look, this beautiful polynomial that you all love so much has a nice first derivative, a really nice first derivative. There's the velocity. But the second derivative is no good. We paid. Mathematics caught us. It said, you got away with 1 derivative, but I'm not going to let you get away with 2. That's bad. So this blip, which violates the common belief that it's monotone decreasing, is saying, if the belief is correct, then we got hit. We got hit by the interpolation process. So instead of a polynomial, let's do what everybody's told. Let's do a C3 cubic spline. Piecewise cubic between the things. I mean, the second derivative is piecewise linear. Even the piecewise linear second derivative has a blip. Even the piecewise linear thing blips. Look, straight, up, down. What is happening, the second derivative is not monotone decreasing, as everybody believes it is. It's supposed to be. So we build a super interpolator. Super. Class C4, piecewise, 5th order curves. The super interpolator. And we use the degrees of freedom to minimize wiggles. And I had a postdoc who was working on this thing. And it still wiggles. Now, at this point, what you do, you go to experts. So I went to the physicists on campus, and the physicist said, no, it shouldn't do like that. So I went to Carl DeBoer, world expert in interpolation. DeBoer says, Richard, there's a mistake in the data. You got noise in the data. It's not supposed to do that. Carl, I'm not sure. So everything we tried, it always had the wiggle. So instead, let's try to explain the wiggle. Let's explain the wiggle. Let's not listen to the physicists. Let's not listen to de Boer. Let's listen to what essentially comes out. Let's say it's there. It's there. And we're going to learn something about the process. Okay? So the experts say, there's noise in your data. Our response, no, we don't believe so. Because we've looked at it and looked at it. And it doesn't matter how we interpolate, we get that blip. So let's go in. And this time, try to change our approach and see if we can explain the blip. So look, let's look at factors on acceleration. Let's just sit down, and which I loved this morning when Arlie Petter spoke. I mean, he went to first principles in building the model. He didn't just say, well, here's something that somebody's conjectured. He went right at definitions, right at first principles. So we're going to start looking at what enters into the acceleration thing. Well, certainly irregular asphalt surface. It's not flat. Soft, spongy, wide tires, low tire pressure, the burnout with hot, gooey, and sticky tires. These four things are going to impact mu. There's no doubt about it. They're going to give us a higher coefficient of static friction. Indeed, I mean, low tire pressure, it's harder to slide. Burnout, gooey and sticky, it's pulling back. Soft, spongy tires, it's pulling back. Non-smooth surface, it's acting like a spur gear. So basically, those four factors tell us that mu equal to 1 is not right. So here's the effect, is basically that, in some sense, it's not like a smooth surface on smooth surface. It's like two gear drives, gear on gear. And in that, we're going to head in that direction. Now, other things that people do, popping and slipping the clutch, spinning the wheels. These two factors do not contribute to increasing the value of the coefficient of friction. But any driver will tell you you have to slip the clutch and you have to spin the wheels. Okay? Why? Popping the clutch allows the dragster to realize an instantaneous acceleration of mu g at time t equals 0. In other words, you pop the clutch and it goes bang. Okay, it didn't go into it slowly. It went bang. So I started my maximum acceleration at time t equals 0, and our data supports that. So you pop the clutch. You don't pop the clutch, you come off smoothly, your car will last longer, and you'll lose races. So the proper slipping of the clutch is an incredible art. Proper slipping of the clutch and or spinning of the wheels are crucial for good acceleration. They allow the engine to operate immediately in the optimal part of its power curve. These engines are running 7,000 RPM. You can't go slowly to 7,000. You pop the clutch and you slip, and the engine gets to 7,000 immediately. So you have to have. So basically, the engine and the wheels are going faster than the car. 7,000 RPM, clutch slipping, wheels spinning, they're going faster. That allows the engine to run in its high power range at 7,000 RPM. But that's not changing mu. That's just telling you why you do those things. So here's, to quote a very famous driver named Bobby on his world record run. I knew it was a great run because the tires were just beginning to haze all the way down the strip. I was just to the point where the tires were starting to slip. This is a world record run. Amount of wheel spin is extremely difficult to control. You start to put a little bit of it, then they go crazy, and you lose it, and you lose control of the car. Here's a fact. You slip the clutch until the wheels begin to spin. Extremely effective thing to do. But how do you control it? Idea, let an analog computer control the clutch slipping by monitoring the wheel spinning. Now, this is an obvious idea. Gary Ormsby and others in 1990s did it. It was so successful that it was outlawed by NHRA. Okay? It took the sport out of the racing. The analog computer is controlling how much you slip the wheels. No, we're going to have to leave it to people. We have to leave it to people. So back to explaining the blip. Let's look at two factors. Let's consider the force F that the dragster's rear wheels apply to the asphalt. And let's write into this ordinary and extraordinary that we get into it. Okay? The ordinary forces represents the force that would result if none of the previously described 6 acceleration factors were present. If none of the things that I said, you just rolled off and you got into it. The extraordinary force represents the force due to the 6 acceleration factors. Okay? So we're going to separate into two things. Ordinary acceleration, extraordinary acceleration. Put it together, you get ordinary plus extraordinary is the acceleration. So it goes across like this. Now let's remember Rosberg. What Rosberg really was saying is that the ordinary acceleration is bounded by 1g, but he didn't account for the extraordinary acceleration. So here's what happens. If we try to look at what, these are just my ideas of what it would like. The ordinary acceleration is kind of like Rosberg said. You roll off, you start to accelerate, You go up to your maximum, and then you go down. But the extraordinary one, from all those other factors, very high, and then goes down to 0. Now, if you take the ordinary and the extraordinary, these two curves just like this, and add them together, you get a curve that looks just like this. So the fact is that we're getting the blip because of the extraordinary acceleration that Vosburgh ignored. Okay? So, no, I don't want to see. I don't want that one. So the blip results because the extraordinary acceleration is so incredibly large at the start and decreases so fast. There's a pulse. I mean, there's an input that just comes in there very strongly. Conversely, the existence of the blip validates the incredible initial acceleration. Okay. Now, here's essentially the ordinary acceleration on this world record run. And here's the extraordinary. Now, you're saying, can you prove that that's what those curves look like? And I say no. But I think that this is part of the explanation of my theory. Ordinary, extraordinary. You add them together, you get that curve. Okay? You get it. So this accounts for the blip. This accounts for the blip. So we think that we have in some way accounted for the blip. Now, here's an interesting experiment. Here's an interesting experiment. That first data point, which is so incredible that the car got there so fast, throw it away. Take out the first data point. So that means that the first 60-foot time you throw away. And that means you let the interpolation tool average the acceleration over the first two intervals. Not just the first one, but over the first two. If we do that, and we average the acceleration that the car needed over the first two intervals, the blip is gone. The blip is gone. It's smooth, and it comes down. So basically, it's this incredible acceleration from that first interval that is incredible, and it accounts for the blip. So we throw that. If we took the second point away, it'd probably come down really nice like this. Okay? So it's that first 60 feet of the race that accounts for all this phenomenal behavior and unusual behavior. That first 60-foot mark. So we believe that we have explained how mu, coefficient of static friction, can be as large as 7. And the acceleration can be as large as 7. We claim that there are two components to, if you use this model, there's two components. Vosburgh made the mistake of ignoring this component, equivalently setting it equal to 0. His theory is fine. Indeed, it's Newton's second law. Okay? Moreover, the assumption that mu 0 is less than 1, that's okay. However, for today's dragsters, mu extraordinary is as large as 6. And it's unbounded in general. So you can't come up with a formula that says how fast can internal combustion engines get down the strip in a quarter mile. It's going to be a function of the technology of tires. The most significant thing in drag racing was when Goodyear decided to get into the tire market. When the big companies said, we're going to go in. That's when land speed records were set. That's when drag racing records were set. That's when everything was set. As long as we were left to backyard companies, we were limited. But when Goodyear got in, when all the big companies got in and said, we'll build you quality tires, world record just fell. And that's in land speed and in drag racing. Okay, so where do we go from here? Well, here's Kenny Bernstein and the Budweiser King that you see on television all the time. Well, quicker and faster. What else? Thank you. According to the clock, we have some time. Okay, good.
So what if you fit the splines to other runs, not just this one?
Oh, I did. Thousands and thousands and thousands. Absolutely. The blip is real. It lives. Absolutely. In fact, Carl de Boer and I had these hard words, okay? But he was so excited that if you look at MATLAB 6, and when he has his interpolation tools, he has various data sets. And one of those data sets is that run. And he says, courtesy of Richard Tapia. And Carl said, this thing caused me so much frustration, I'm going to share it with others. Okay? Yeah, the answer is, yeah, it's there. Now, it's not going to be there for a slow car. It's not going to be there for, whatever you drive going down a quarter mile. It's not going to be there. You will not have a blip. You do not own a blip, okay? But anybody who runs a world-class dragster has a blip. Okay?
Any other questions?
Yeah.
Just kind of, it was just kind of an observation. Maybe you have some more words you can say about this. The early data, the response to the early data seemed to show that actually some theoretical boundary was being breached. It seemed like the sort of the quote mathematician at the time's response was, well, there must be something wrong with your data. We still do that a lot, don't we?
Yeah, we do. We do. See, I mean, look. I mean, De Boer and I are really close friends, and he's really good. And yet Carl wouldn't give in. I mean, he said, Richard is not going to do that. And then I have a consultant who's a physicist at Rice, Steve Baker, and he said the same thing to me. And I one day, after, I did exactly what you said, Carlos. I ran hundreds of them. And I said, hey, I mean, I can't be stupid forever. Okay.
We know that Bobby has a big blip.
Yeah, Bobby has Bobby is a big, Carlos, Bobby's a big blipper, yeah.
What about you?
No, I mean, I'm not a driver, okay? I mean, I was support to Bobby, okay? And it was wonderful in doing that. But there's other things. I have like 5 or 6 other topics that we can explain in mathematics. And one of them is, basically I'll share with you, is since you use a finite difference approximation for calculating the velocity, people believe that, rightfully so, that the car is going faster than the time you get. Okay? So everybody says, oh, the car's going faster. So when somebody ran 296, everybody says 300. And that's true, because basically the second derivative positive makes it a convex function. So when you do a first difference approximation, it underestimates. Okay? So we do some analysis on that and show that basically it's in the 3rd decimal place. Okay? It's almost exact. Yeah. And there's others and stuff and things like that. They just, Cynthia?
Is there anything else where people are subjected to 7G?
You can only be subjected. See, one of my dear friends, Jim Peterson, works for NASA. In fact, he deals with that. And he said that if you had that over a long period of time, you'd black out. So this is instantaneous. This is instantaneous. And it can't be for a long time. In fact, if technology gets better, let's say the Goodyear decides we're going to build the ultimate tire and you're going to hold 7 Gs for 3 seconds, okay, 2 seconds, okay, then we're going to have drivers passing out and getting killed. So as technology goes forward, the safety constraint. So, round off error, okay, so we always have a rounding error going one way, and basically what we get from finite, expansions, okay, so basically we have the rounding error and truncation error. Okay? That's what's happening here. Technology and safety going against each other. Okay? Can you do it for a long time? Okay? Yeah. Bobby, do you ever feel anything at the initial start and then it goes away, or what do you think?
No, I think that the majority of it is that you kind of position yourself for that. I mean, yeah, it's obviously, I guess the best analogy I can use is, has anybody been on a roller coaster where it's a free fall?
Yeah.
Well, it's a lot faster. It's a lot more, you get more push than you do on that. That's the closest thing I can relate to.
Yeah. But I think that there's already concern that if you held it too long, you're going to have drivers passing out. And that's what Jim Peterson says from NASA. So we got to worry. Yes?
Yeah, you mentioned something about that. Those last 2 pieces of data.
Yeah.
And you said that it seemed like very close, I think, time.
Yes.
It was something about how they measured something. I can't remember that.
Yeah, well, see, what you do is that, you have the data in terms of distance, and so you want to estimate the derivative. So what you do is a finite difference approximation. So you take, and everybody knows that if you want to make your finite difference approximation accurate, you'd have the data points close together. And that's why those 2 points are close together. It used to be that the central difference is far superior than the forward difference, okay? So they used to have a clock in front of the finish line and after the finish line. But the insurance companies made them take it away. They said, everybody knows that, so the drivers are keeping their foot in the car until they pass the finish line, and it's creating a lot of danger. So the insurance company said, take out the last clock and put it in the quarter mile. Okay? So the insurance company says, you can't use the central difference, you have to use the forward difference. That's what the insurance company said. Okay?
Any other questions? Oh,
Yeah. Nah. But Mark, this is a good question, because let's go back to Joseph's talk. What killed muscle cars? They died in 1970. They died. What are the factors that kill them? Okay? A major factor, in fact, probably the biggest one, were insurance companies. They killed them. General Motors got out of racing. Insurance companies said, you can't do that. And the other one was pollution control. But the biggest factor in killing muscle cars that we used to build in the 60s was insurance companies. All right.
One last question. Should they put more data points?
Yes, yes. And I've asked them, and they say they will do it. Okay? So we have friends. Bobby and I have friends. Steve Gibbs. Okay? Sharp. What's Greg Sharp? So they say, sure. All you have to do is write a letter saying you're doing some experimentation in the name of research at a university, and we will do it. But we won't tell the racers about it, and we'll get it. And they have agreed to do it, and it'll tell us a lot. But they haven't done it. So I have to get back there and be...
Slide will be a bunch of open questions that people might want to work on if they get interested. Okay, so what is communication complexity about? Well, abstractly speaking, you can view it as sort of the intersection or the combination of information theory type questions with complexity theory type questions. And in fact, because of this characterization, we will see a lot of connections with earlier talks, because those earlier talks dwelt on quantum information theory and quantum complexity theory. So before choosing whether we look at classical or quantum, let's state a problem. So there are two parties, or two processors, or two planets, or whatever. They're sort of spatially separated, and they want to do some distributed computation tasks. So there's an input x, y, an n-bit string x usually, and an n-bit string y usually. And now they want to compute, Alice and Bob together want to compute some function which depends both on x and on y. So it's distributed computing. The input is distributed over various places. And the only complexity measure that we're interested in this model is the amount of communication that Alice and Bob need to send to each other. So the number of bits in the classical case, the number of qubits in the quantum case. So in general, there is some function depending on x and y that they want to compute. Let's assume by convention that Alice starts out. So Alice looks at her input x, sends some message to Bob. Bob looks at that message, looks at his input y, sends some stuff back, and so on. This can go on for any number of messages. And then at the end of the day, they should have communicated enough information to enable them to output the function that they want to compute, this f, which depends on x and y simultaneously. Let's say that we want both Alice and Bob to know that value at the end of the protocol. So this is a fairly well-studied problem classically. It was introduced more than 20 years ago by Andy Yao in 1979. And a very good book, a slender but sharp volume about the classical aspects of communication complexity is the book by Kushilevich and Nissan, which I can recommend to anybody who wants to learn about this stuff. So a few comments about this problem here. So notice that I'm basically considering only n-bit inputs for x, n-bit inputs for y, and a Boolean value as output. This is, of course, a limitation. You could also consider computing something from a larger range, which has been studied too. And apart from Alice and Bob wanting to compute some function, you could also consider other computational tasks. For instance, maybe Alice and Bob don't want to compute something, but they want to sample from some joint probability distribution. Also, for that case, you could ask how much communication do they need to send to each other in order to enable them to sample. I will not discuss those extensions. I'll just discuss this simple computing a Boolean function. So let me put this on the other overhead projector, because this will be the problem setting for the rest of the talk. So a simple example of classical communication complexity, just to show you an example of the model and also an example of a non-trivial protocol. So sort of arguably the simplest non-trivial or one of the most natural distributed computing tasks that they may want to solve is just to determine whether Alice's input x is equal to Bob's input y. So x and y are each n-bit strings. Alice holds x, Bob holds y. And they just want to know whether they have the same thing or not. So the equality function is defined to be 1 if and only if x equals y, and it's 0 otherwise. So it's not hard to show that classical deterministic protocols are basically no better than the stupid solution of just sending x across. So notice that you can always solve a communication complexity problem just by letting Alice send the whole x to Bob. This takes n bits of communication, but it certainly enables Bob to compute the function value because he has anything that he wants now. And it turns out that for classical deterministic protocols, that's the best you can do. N bits of communication are needed too. As an example of what classical randomization can buy you in this model of communication complexity, let me give you a much more efficient randomized protocol, which only needs to send a logarithmic number of bits. In fact, there's only one message there. Oh, yeah.
Are you presuming x and y are chosen randomly or chosen adversarially?
So this is worst case complexity. They're chosen adversarially. The protocol should work for any input pair x, y. Yeah, otherwise equality would be fairly simple, of course, because almost all inputs are far apart and therefore easy to distinguish. But in any case, in the randomized case, there exists an efficient protocol that works for all inputs with very high probability, and it just needs a logarithmic number of bits of communication. Okay, so here there are many different ways to achieve this. It's basically hashing. Let me give you one example of a protocol. So Alice associates with her n-bit string x a polynomial p sub x, a univariate polynomial in some value z, where she uses the n bits of x as the coefficients of the polynomial. So it's a polynomial of degree n minus 1 in z. So, for instance, if x would be 1, 0, 1, you would have 1 plus 0 plus x squared. It's a degree n minus 1 polynomial. And then so in advance they determine some field f of decent size, let's say of size 10 times n. N is the input length. And then given this association between n-bit strings and polynomials, here's a protocol that will allow them to determine whether x equals y. So Alice picks a random element z from this field here, and she sends the description of that z and the value of her polynomial on that z to Bob. So z is an element from a field of about this size. It just takes a logarithmic number of bits to describe. And if we're working over this finite field, then also the value of the polynomial will be an element of the field and therefore have a logarithmic description. So the total message here, z and this polynomial value, is just like twice log n many bits. So this is what Alice sends to Bob. And now Bob is going to compare this value here with the value of his polynomial p sub y on that same field element. So Bob just computes p sub y of z, which he can do because Alice has sent him z, and of course he already had y because that's just his input. So he can compute this value, and he can compare it with the polynomial value that Alice sent him. And then he just outputs whether those two values are equal or not. And this solves the equality problem with good probability, because in the first case, if x happens to be equal to y, then clearly the polynomial px is equal to the polynomial py. These are really identical polynomials, so no matter which value z you plug in, you will get the same value. And Bob will output that x and y are equal, which is correct in this case. If x is different from y, then we get the phenomenon that has been mentioned earlier, that two low-degree polynomials cannot, two distinct low-degree polynomials cannot have the same value on many points. So px and py are polynomials of degree n minus 1. And therefore, if you look over the whole field, then out of these 10 n elements, at most n minus 1 different z's can give px and py the same value. In other words, for almost all z's in the field, for about 90% of the z's in the field, these two things will be different. And Bob will detect that. So with just a logarithmic number of bits of communication, they can solve the equality problem with very high probability. So this is a simple example of classical communication complexity. So what is quantum communication complexity? Well, what could it be otherwise than just giving Alice and Bob a quantum computer and a quantum channel? So this is a very natural question to ask if you know about classical communication complexity and you know about quantum computers. So what happens with communication complexity if Alice and Bob have a quantum computer? Can they compute some interesting functions with much less communication than they can classically? Turns out that the answer is yes. However, there is a fallacious argument that tells you or suggests that there's nothing to be gained here. The argument comes from Holevo's theorem, which was mentioned by Ashwin on the first or the second day. And in fact, he proved this, a weak version of this theorem. So Holevo's theorem tells us that k qubits, for instance, a message of k qubits, cannot contain more information than k classical bits, information in the Shannon sense of the word. So, well, this sort of suggests that there is no improvement possible from classical communication complexity to quantum communication complexity. If the classical protocol needs to send k bits, then you would think that, well, any quantum protocol will also need to send k qubits, otherwise it would violate Holevo's theorem. And that's a wrong argument. The reason being that there's no reason for Alice to actually send, or for Bob to send k bits of information. The only thing they're interested in at the end of the day is one bit of information, namely the function value f as a function of x and y. So this information theory argument suggests that there's nothing to be gained, and that's wrong. And there are some interesting examples where quantum communication complexity is much, much lower than classical communication complexity. Yeah, so let me just give you a number of those examples. Maybe I should say that this was introduced by Yao, Andy Yao, the same one who introduced classical communication complexity. Not because he was interested in getting good quantum protocols, but because he was interested in proving lower bounds on other models. And that's, in fact, one of the motivations for studying quantum communication complexity. So before embarking on a number of good examples of good protocols, let me give a little bit more motivation. So why study quantum communication complexity? Well, it's just a nice model of distributed computing. It's natural, it's abstract, it's elegant. There's just one complexity measure that we're interested in. So you can just view this as a mathematical problem, abstract it from a real computational context. So that's one reason, and that's, for me, that's the main reason. But for other people who are more interested in applications, is that you can use quantum communication complexity, or you can use communication complexity in general, to prove lower bounds for other models. The reason being that many settings which are very different from communication complexity involve some communication complexity problem as a part of its setting. In other words, if, for instance, if you have a chip and you know that somewhere on the chip needs to know whether the left half of its bits are equal to the right half of its bits, that's actually the communication problem equality. And if you have lower bounds on how much communication you need, you get lower bounds on something about that chip. For instance, how many wires should go between the left and the right half, or something about the trade-off between its area and the time it takes for its computation. So that's another motivation. A third one, which is of a slightly more philosophical nature, is that quantum communication complexity shows differences between the classical world, the classical computational world, and the quantum computational world. Differences that are both provable and that are in a realistic model, in the sense that you can actually envision people doing this in the real world. There's nothing hidden there. And this is opposed to separations that are known for black box algorithms. For instance, it's known that Simon's algorithm solves a black box problem exponentially faster than any classical algorithm. However, these black box algorithms are not realistic, because however way you want to implement that black box has to be given to Simon's algorithm as not really as a black box, but as some kind of circuit. And in that setting, the classical lower bound would break down. It's always possible that a classical algorithm looks at that circuit for the black box and does something really smart with it, which it would not be able to do in the black box setting. And this is not the case with communication complexity. There's nothing hidden there. It also, in really proving exponential quantum classical separations, it does something which is, in a sense, better than what Shor's algorithm for factoring does. Well, I mean, factoring is clearly the main result we have in this field, but it's not a proven separation between quantum and classical, because nobody can prove that there's no classical efficient algorithm for factoring. In fact, such a result would imply that P is different from NP and would gain the author at least $1 million, and yet nobody has done that. So quantum communication complexity gives you an example of a quantum classical separation that's proven as well as realistic. And that's something that's not the case for most other examples of quantum power. Another example, for instance, is John Waters's result about constant message quantum IP, which contains p-space. Now, we expect that constant message classical IP does not contain p-space, but that's again something we cannot prove. Okay, so let's move on to examples which show communication problems that can indeed be solved much faster if we have quantum power. So I'm going to discuss 4 examples of such protocols, and the first 2 of those are derived from black box algorithms. The first and the simplest one is the example of the distributed Deutsch-Jozsa problem. Let me first say what the Deutsch-Jozsa problem itself is. Probably Mike mentioned it on the first day of the workshop. So this is a black box problem where you're given in the form of a black box a string of n bits, x1 up to n. Let's say that n is even. And you're given this in a black box fashion, meaning there's some black box, you can put some number I in it, and out comes the bit xi. And a quantum computer can run this thing in superposition. And the computational problem to be solved, the function of this input, is this string here constant, let's say all 0, or is it balanced, meaning that it has exactly as many zeros as ones? And the Deutsch-Jozsa quantum algorithm solves this problem with only one quantum query and log n additional quantum operations, whereas any deterministic classical algorithm would require n over 2 separate queries because it has to look at most of these bits separately before it can distinguish all 0 from half 0. So that's the Deutsch-Jozsa problem. And now you can take a distributed version of that. So instead of having one input, we now have 2 inputs, x and y. We're going to give x to Alice and y to Bob. There's no black box anymore, so they just get these things in their hands. Alice gets the n bits of x, and Bob gets the n bits of y. And now the question we're asking is, are x and y equal, or is their Hamming distance n over 2? And notice that this distributed question is basically the Deutsch-Jozsa question applied to the XOR of x and y. Right? If x and y are equal, then their XOR is just the all 0 string, the constant case. And if x and y are a distance n over 2, then their XOR has as many zeros as 1, so then you're in the balanced case. So this is really a distributed version of the Deutsch-Jozsa problem. And it can basically be solved by taking the one query Deutsch-Jozsa algorithm and turning that one query into a short quantum message. So we're basically simulating a query with a little bit of quantum communication. So here's the efficient protocol. It's due to Burman, Cleave, and Victorson from '98. I'll be a little bit scant on the reference here. If you want to know more, you can ask me afterwards. So here's a simple yet efficient quantum protocol for this problem. So Alice has x, which in particular means that she can just construct this quantum state here. She can take a superposition over all the indices 1 up to n and put the bit xi, all of which she just holds in her hands. She can put those in the phase. And this message she can send to Bob. Notice that since this is an n-dimensional quantum state, we just need log n qubits to represent this thing. So this is really a short message. So Bob gets this thing, and then he looks at what his y is, and he tacks on another phase. So he basically does this mapping here. I maps to -1 y I, which is clearly unitary. In fact, it's a simple diagonal matrix. So Bob applies this operation here to the state that he receives from Alice, and that turns the phases into -1 to the power xi plus yi. And notice now that this is exactly the state you would have if you would run the Deutsch-Jozsa algorithm on the string x or y. And now let's analyze what Bob has, whether he can find out whether x equals y or is different from y. So first case, x is equal to y. Well, in that case, these phases disappear because this exponent here will be either 0 or 2, and Bob will just have the uniform superposition in his hands. In the other case, notice that we have a promise problem here. We only consider 2 possible kinds of inputs instead of all possible kinds of inputs. So the other case of the promise, where the distance between x and y is n over 2, in that case, you will, in this n-dimensional superposition, you will have n minus 1 ones and n minus 1 minus ones, which means that if you take the inner product of that state with the uniform superposition, you will actually have an orthogonal state. In other words, what Bob can do is he can take this thing psi, project it basically, make a measurement that projects it onto the uniform superposition. If that measurement says yes, then he knows that x must be equal to y. If that measurement says no, then he knows that psi must have been orthogonal to the uniform superposition, and he knows that he's in this case. So here we, in fact, have an efficient quantum protocol for this problem. It just takes log n qubits of communication, and it solves the problem with probability 1. In contrast, you can prove that classical deterministic protocols for the same problem need almost n bits of communication. And this proof is non-trivial. It's based on a combinatorial result of Frankel and Reudel about set systems where the sets are not allowed to intersect in a specified number of points. And this is, in fact, a general pattern in all the examples that I will show. The quantum protocol is relatively easy, fits on half a slide. The classical lower bound, as you need to prove a separation, is much, much harder. In fact, if you look at most quantum communication complexity papers, most of their time is devoted to proving classical lower bounds. So, because in order to prove a separation, we need a quantum upper bound and a classical lower bound. Okay, one thing to notice about this problem is that if we allow a little bit of error probability, it's very easy to solve. Alice can just pick a few i's at random and send those over together with the corresponding bits xi at random. Bob just checks whether those bits are equal to his bits at the position I, and this will determine with high probability whether x is equal to y or whether it's different in half of the places. Because a random position will be different, xi will be different from yi in the second case of the promise. So this quantum classical separation is exponential. It's log n versus n. But it disappears completely when you allow some error probability. So the second example remains valid also if you look at classical bounded error protocols. So this is the disjointness problem. It's one of the key problems in communication complexity, and I'll come back to it later. The problem is simple to state. So we view the n-bit string x as representing some subset of an n-element universe. So x is just a characteristic vector of a subset of the set 1 up to n. Similarly for y. So Alice gets a set, Bob gets a set. And now the question they want to answer is, are these sets disjoint or not? And it's a known as well as hard result from classical communication complexity that a classical protocol needs to send almost n bits. So the stupid solution is basically optimal for classical protocols solving this problem, even for classical protocols that are allowed some constant error probability, like a third or so. However, if you slightly massage this problem, then you immediately see that there's probably a good quantum solution, because a different way to state this question here, whether x and y are disjoint, is does there exist some element I where both xi and yi equals to 1? In other words, does there exist an element I that's in x, the x set as well as the y set? Now this is a search problem. We just want to search among all n possibilities whether such an element exists. If you think about search and you think about quantum, you think about quantum search. And for that we have Grover's algorithm, which runs quadratically faster than the classical algorithms. So again, Burman, Cleave, Victorson observed that they could take this black box algorithm, Grover's algorithm, simulate each of its queries by a small amount of quantum communication, about log n qubits, and get from that a distributed version of the search algorithm that basically finds an intersection if there exists an intersecting point for x and y. So Grover's algorithm takes about square root of n steps, queries that is. Each step takes about log n qubits to simulate, because the query register is just a log n qubit state. So basically what happens is Alice runs Grover's algorithm. Whenever she needs to make a query to the string x and y, she prepares her part of the deal, sends it over. Bob prepares his part of the deal, sends it back. And now Alice has effectively made a query to the end of x and y. And notice that there will be an intersection between x and y if and only if there's one position where the bitwise end of xi and yi equals 1. And that's what Alice is searching for using Grover's algorithm. So a distributed version of Grover's algorithm solves this problem here with about square root of n qubits, a little bit more, because of the reduction. You can in fact get rid of most of this log n factor here. So Peter Hoyer and myself, we slightly improved this upper bound to this upper bound, where log star is defined to be basically the height of the, if you build a tower of 2, so 2 to the 2 to the 2 to the 2 to the 2, and how high does the tower need to be to reach n? That's what log star is. It's an extremely slowly growing function. And therefore c to the power, so c is a constant, c to the power log star n is also an extremely slowly growing function. So for all practical purposes, if we can speak about that here, that's a constant function. And it turns out, as I will mention later, that this, without this log star fiddling, is actually optimal. Okay, so we've seen an example, namely this distributed Deutsch-Josa, where an exact quantum protocol is exponentially better than an exact classical protocol, but the advantage disappears if we allow bounded error. We've seen another example of a bounded error quantum protocol that's quadratically better than any bounded error classical protocol. And then Ron Ras came along and combined the two features of those two separations. So he proved, or he exhibited a problem where a quantum protocol is exponentially better even if we allow the classical protocol to have some error probability. And here's the problem. I'm not going to say that it's a useful problem or that anybody would ever want to compute this, but for a theoretical computer scientist that doesn't really matter. So the problem is as follows. Alice gets some vector v in n dimensions. Let's say it's a unit vector. And she gets a decomposition of this space Rn into two subspaces. And let's call them M0 and M1. And then Bob gets a unitary transformation on the same space. And the promise is, so again, we're not considering all inputs. There's a promise here. The promise is that if you take the vector v and you apply u to it, then the resulting vector will be either completely in this subspace or completely in that subspace. And the computational question that they want to solve is it M0 or M1? So that's a Boolean function with a promise. So the way I stated it, the quantum protocol is basically, well, it's basically a restatement of this promise here. So here's the protocol. Since this thing here is a unit vector, a unit vector in n dimensions, that's just saying that it's a quantum state of log n qubits. So Alice can just view this vector here as a quantum state of log n qubits and send that over. And then Bob, who knows u, can apply u to v and send the result back, which is still only log n qubits. Now Alice gets this thing here, and she makes a measurement distinguishing M0 from M1. And since we're promised that this vector here either lies completely in this subspace or completely in this subspace, this measurement will tell us the outcome with probability 1. There's no error probability here. Notice that I've stated this as a continuous problem, but you can easily turn this thing into bits by approximating each real number by something like log n bits or so. So there's a very efficient quantum protocol with just 2 rounds of communication for this problem. A classical protocol, on the other hand, needs a polynomial number of bits. I think Ras's best result is n to the 1 over 4 divided by log n bits. So this is 2 log n qubits versus n to the 1 over 4 bits. And this even holds if we allow error probability for the classical computer. And this again is a pretty hard result, whereas this is a very easy result. So quantum results tend to be easier than the classical lower bounds.
Except when you try to prove lower bounds.
Yes, yes. There you get the worst of both worlds. Okay, a fourth example. Is what's called fingerprinting. Which may or may not be a misleading name, but let's just use it. So before describing the communication complexity problem we're going to solve with fingerprinting, let me explain what fingerprinting is, or rather what quantum fingerprinting is. So this was done by Burman, Cleve, Watrous, and myself last year. The idea is that let's look at the space or the set of all n-bit strings. There are 2 to the n of those guys. And let's associate with every n-bit string x a quantum state phi x in such a way that the vector phi x and the vector phi y have small inner products. In fact, it turns out that we can do this in a very low dimensional space. In other words, we have 2 to the n different x's, and yet using about n dimensions, we can give vectors phi x, which are almost orthogonal. Notice that it's not possible to do this with if you replace small by 0, because then you would just embed a 2 to the n dimensional space in a 2 to the n dimensional space. So it is possible to associate with the classical n-bit strings quantum states of about log n qubits that are almost orthogonal. And I guess I have enough time, so on the next slide I'll actually show you how to do that. An explicit simple construction. So why are these things called fingerprints? Well, so phi x is a pretty small quantum state. It's just log n qubits, which means in particular that it will not have a lot of information about x. That's again Holevo's theorem. However, if you just care about checking identities, checking whether x equals some y or something, then it turns out that instead of requiring x and y themselves, it suffices to have the 2 fingerprints. So if you have phi x and phi y, then I can tell you with a simple test with good probability whether x is different from y or not. The way it works is just to use the swap test that John Watrous spoke about before lunch. Because the states phi x and phi y will be either equal, namely in the case where x equals y, or they're almost orthogonal, namely in the case where x is different from y. And we can actually test that using this thing called the swap test. And now you can basically build a communication complexity story around this, and you get this communication complexity problem, which is efficiently solvable with a quantum computer. It's an instance of the equality problem again. Alice gets x, Bob gets y. But now we change the setting a little bit in the sense that there's no longer any kind of two-way communication allowed between Alice and Bob. Instead, there is now a third party, which is called a referee. And Alice has just allowed one message to the referee, and Bob has just allowed one message to the referee. And now the referee needs to determine whether x equals y. So the referee wants to compute the equality problem. For instance, think about Alice and Bob being each in their separate spaceship, floating around space, each on their own side of the universe. And then the command center on Earth wants to know whether they've assembled, whether the pieces of data that they assembled, Alice's x and Bob's y, are actually the same or not. So the referee, for some reason, is interested in computing the equality problem. Now, fingerprints allow you to do this very efficiently, right? Alice just sends the quantum fingerprint for x. Bob just sends the quantum fingerprint for y, which are really small states, just log n qubits. And the referee implements this swap test, and he can determine whether x equals y or not with good probability. And if you want that good probability to be an even better probability, then you just let Alice send 100 copies and Bob send 100 copies, and you repeat the thing 100 times. So there's a cheap quantum protocol that solves this complexity problem. So I've shown you in one of the first slides a very efficient classical protocol to solve the equality problem. Namely, Alice picks this polynomial, plugs in a random value z, sends over z and the polynomial value to Bob, and Bob checks the identity of the two polynomial values. That protocol is not going to work here because there's no way for Alice to communicate to Bob which random z she picked. So that protocol is not going to work in this setting. You might think there might be something else that works, so some sort of classical protocol that solves the same problem with just log n bits of communication, and that doesn't exist. And again, the proof of that result is much harder than the proof of the quantum upper bound. So Nisan and Szegedy, in the early days of quantum computing, when they probably hadn't even heard of quantum computing, proved that a classical protocol needs about square root of n bits to solve this problem. So again, an exponential separation, and even for a very natural problem, the equality problem, the downside of this result here is that it only holds in this very restricted model of communication complexity where Alice and Bob don't communicate directly. And as I mentioned, the main ingredient in the quantum upper bound is this mapping here from n-bit strings to log n qubit strings that are almost orthogonal. Let me show you how to build that. And there are many ways to get these short, almost orthogonal states, these low-dimensional, almost orthogonal states. And given the structure of this talk, the easiest way to get it is using the same polynomials that I've already used before. and basically putting their values in superposition. So again, let's associate with every n-bit string x a polynomial p sub x of z, exactly the same as before. You just use those bits as coefficients for the different powers of z. It's an n-1 degree polynomial. We fix some finite field f, let's say of size about n over epsilon. Its size has to be a prime power, but we can just round stuff. And now let's just make a superposition of the different polynomial values. So let's define a fingerprint phi of x to be a uniform superposition over all field elements of a two-register state, z, and a polynomial value on z. This is a very short state, right? Because for the same reason that the classical protocol from one of the first slides was efficient, this guy just takes log n bits, this guy just takes log n bits. So our superposition takes about 2 log n qubits. And now I need to show that these things, these short quantum states, indeed are almost orthogonal for if x is different from y. And the reason that's the case is basically for the same reason that the classical protocol for equality worked. If px is different from py, then for most field values, for most z, px of z will be different from py of z. In other words, if you just take this thing with x and you take this thing with y, you compute their inner product, then that inner product is upper bounded by the number of points in which they intersect divided by the field size. And since these are degree n-1 polynomials, there are at most n-1 elements. Is that right? Maybe n elements where they intersect. And since we've chosen the field to be of size n over epsilon, the upper bound on the inner product between two states is at most epsilon. So this is a simple way to construct short, almost orthogonal quantum states, which can be referred to as quantum fingerprints, right? I mean, just as your fingerprint is sort of a very short description of you, which is useless for most purposes, but it suffices if you want to check identity between two people. If I have my fingerprint and I have Ashwin's fingerprint, we can check whether we're the same or not, even though those fingerprints don't tell us very much. Okay, so those 4 examples that I've shown are most of what's known in terms of upper bounds. There's not much more good news at the moment. As is the case with quantum algorithms, there are just not many good tricks that we know. So let's move on to the downside. Let's move on to lower bounds. So as Ashwin mentioned, you can prove lower bounds for classical protocols, but you can also prove lower bounds for quantum protocols. And that's often a hard problem. I guess there's basically only one non-trivial lower bound for quantum communication complexity that fits on one slide. And that's the one I'm going to describe here. It's really very elegant. So the lower bound concerns the inner product problem, which is defined to be the inner product modulo 2 of the n-bit string x and the n-bit string y. And if you remember, the Michael Ben Orr's talk from yesterday actually assumed the hardness of this problem for his security proof for key distribution. In other words, the lower bound that I'm going to prove is sort of the foundation of one of the proofs that quantum key distribution is possible. And that wasn't a very unexpected connection between quantum communication complexity and quantum cryptography. So apart from being a pretty proof, it's also a useful proof. Okay, so we want to prove a lower bound on the number of qubits that a quantum protocol needs to communicate between Alice and Bob in order to compute this function here. So let's assume we have an arbitrary protocol that computes this function. And let's assume it uses m qubits of communication, right? We want to show that m is large. So this protocol can be used to compute the following transformation, which basically the only thing it does is it puts the output in the phase instead of in an extra bit. So if we have a protocol that computes f, I'm ignoring error probability for now. If we have a protocol that computes f, then with the same amount of communication, we can also compute this transformation here, where just the inner product is put in the phase. It becomes a +1 if the inner product is 0. It becomes a -1 if the inner product is 1. So using m qubits of communication, Alice and Bob can implement this joint transformation of the total state. But if we can do this with m qubits of communication, then we can also do this with m qubits of communication on a superposition of inputs. So if we run this exactly the same thing in superposition over all y's, then the final state is going to be this. So we fix x, but we let Bob's input range over all possibilities. And now because this phase factor just commutes with the tensor product, we might as well put it here. And Bob's state ends up like this, ignoring normalization for now. Now anybody who has paid attention in the last few days knows what this thing is. It's just a result of applying a Hadamard transform to the string x. But that means that you can just, again, apply a Hadamard transform and get the string x out of this. In other words, if this is the total state, where this is Alice's register and this is Bob's register, then Bob now has an efficient way, well, even if it weren't efficient, he has a way to compute x. But that means that actually n bits of information have been transferred from Alice to Bob. Using a protocol for inner product in superposition, you can actually communicate the whole x from Alice to Bob. But we know, because of Olevo's theorem and because of Ashwin's theorem, that this takes a lot of bits of communication, even qubits of communication. So if we ignore error probability for now, then the fact that this protocol here can be used to communicate n bits means that its communication must have been n qubits at least. In other words, the communication complexity protocol for inner product that we started with must have used n qubits of communication. There's really nothing smart that can be done here. And the same proof basically works also with a lot of, well, with some more technicalities in case there's some error probability. If there's some error probability, then Bob will receive x with high probability instead of with probability 1. And again, Olevo's theorem says that you need almost n bits of communication and qubits of communication to get that done. Okay. I guess this is the only lower bound that I'll mention in detail, because it's the only one that's mentionable in detail in a short amount of time. There's more known, and that's what is known is much more complicated. Let me just basically mention some of the main lower bounds that are known. So we can distinguish between protocols that are required to compute f with probability 1 from protocols that are required to compute f with high probability, just as there's a difference between P and BPP or between EQP and BQP. The same distinction exists everywhere in computer science.